This is a Math 2 lesson summary video titled How Does It Grow? This is a practice understanding task. The purpose of this lesson is for students to describe the rate of change of a function and practice creating multiple representations. In this task, you're given a series of problems. For each one, we need to identify whether or not the relation is a function, determine if the function is linear, exponential, quadratic, or neither, describe the type of growth, and create one more representation for the relation. For a relation to be considered a function, every input of that relation needs to have exactly one output. Linear functions grow by adding a constant difference, so adding the same value over and over and over to the previous output. Exponential functions grow by multiplying a constant ratio, so multiplying the same value to the previous output to get the next one. And then quadratic functions grow by adding a linear pattern. So you're still continually adding, but the amount that you're adding is changing at a linear rate. So the first difference of a quadratic function is linear. The relationship between the number of dots in a figure and the time t. So let's take a closer look at each figure, and let's start by just recording how many dots are in each figure. So when t equals 1, there's 1 dot. T equals 2, there's 3. T equals 3, there are 6. And t equals 4, there are 10. So I can see how this is changing. We're adding 2 dots at first, and then adding 3 dots, and then adding 4 dots. So there is linear growth because I have a predictable linear pattern. That means we can use a quadratic function to model the growth. And I do know it's a function because for every value of t, there's only one specific number of dots that could be in that figure. Now let's work on creating another representation. In Desmos, I'm going to press the plus button to add an item and select table. If t was 1, 2, 3, or 4. When t was 1, there was 1 dot. When t was 2, there was 3 dots. And then it went to 6, and then 10. Can't see all my dots, so I'm just going to click and drag. And I can see that familiar quadratic pattern where I'm going up 2, then going up 3, then going up 4, and I have this piece of the parabola. If your other representation, if you wanted to create an explicit equation, I'm going to use my strategy of where I double the figure and then rotate it 180 degrees. Now to get the total number of dots, I have the same number of dots in the bottom row as I do for the value of t. And I have 1, 2, 3, 4, 5 rows, so I have t plus 1 groups of t. So there's one group of t, another, that's 3, 4, one more group, then t. Same thing happens here. I have one group of t, and then I have 4 groups of 3. So that is t plus 1. And the same for the other 2. So to get the total number of dots that I have, I'll do t, because that's with one row. And I have t plus 1 rows of t dots. So to get this relationship to work, remember we did have to double the number of dots that were in our figure. So that means for our final answer, we'll need to divide by 2. All right, let's look at one more question. Here in number 11, I have the product of 2 linear factors. So I already know automatically that this is quadratic. Let's go to Desmos and create a table and a graph. So on Desmos, I'm going to type in the equation as it's written, and I'm just going to zoom out a little bit and scroll. It is still a little hard to see, so I'm going to go to my graph settings and change my x-axis. Instead of it going all the way from negative 39.8 repeating to 40.112, let's just take a look between negative 10 and positive 10. Now I can see my x-intercepts and my minimum point. If I wanted to look at the table, I can hit this gear, and then click on the table button. And here I have a table of values. So we can clearly see that this parabola is a function because every input, so here, for example, when x is 0, y is negative 18. If I zoom out and get a look at a lot more of this graph, I can see that every input has exactly one output. Let's return back to this equation. I could also rewrite my equation by multiplying my two linear factors. I'm going to use the box method, so I have 4x plus 3, x minus 6, giving me 4x squared. So now I'm using the distributive property to multiply, and the box just helps me keep everything organized. And I can combine like terms, so I have y equals 4x squared, and then negative 24x plus 3x makes negative 21x, and then minus 18. Now that the quadratic equation is written in standard form, I can see that the largest exponent is 2, again confirming that I have a quadratic function. And since I know that quadratic functions have a linear rate of change, I would describe my type of growth as linear. So again, just to summarize, for a function, every input has exactly one output. Linear functions grow by adding a constant difference. Exponential functions grow by multiplying a constant ratio, and quadratic functions grow by adding a linear pattern. And that's it for this video. Thank you for watching.